Hello students, let us discuss some of the reasoning questions of P block elements. Okay, so first question I have taken for you all is how can you explain the higher stability of BCl3 as compared to TlCl3? So BCl3 is boron trichloride and TlCl3 is thallium trichloride. Okay, so how can we explain the higher stability of boron trichloride as compared to thallium trichloride? Okay. So before understanding this, you should know one word, that is the inert pair effect. Okay. So what is this inert pair effect? Actually, what happens when the atomic number goes on increasing? Okay. So as we go from top to bottom, okay, in a periodic table, we see that yes, the number of shells are increasing. Okay, as the shells are increasing, there is the increase in the d and the f orbitals also. And yes, you know about the screening effect, isn't it? Screening effect, students, you know. So what is the screening effect? In this, actually what happens, we see that yes, the S, P, D and F subshell, they have got different shapes, isn't it? So here you'll be seeing that yes, S has got a spherical shape, yes, P has got a dumbbell shape, D has got double dumbbell shape. So we are seeing here that yes, when the electrons are present in these subshells, okay, what happens? There is screening by these subshells. What is this screening? The effective nuclear charge, okay, is being screened by these subshells, that is the S, P, D and F. Okay, so what happened? Due to the shape, what happens? As it is what? Circular or spherical in shape, most of the screening is done by this S subshell. And yes, SP is dumbbell shaped, okay, and D is double dumbbell shaped, okay, like yes, for making you more understandable, okay, this is the shape of what? S subshell, okay, this you can see is the shape of what? P subshell, isn't it? And when we talk about D subshell, it is what? Double dumbbell shaped, isn't it? So here you can see that yes, here the screening can be done the most, okay, and here because of its shape, screening can't be more appropriate and not to a much larger extent. And yes, in D you are seeing it is totally double dumbbell shaped, F it is undefined, okay, so here screening can't be done properly. So one thing you have understood that yes, what happens, the electrons present in the S subshell, okay, as they are showing the most of the screening, okay, what happens when the atomic number increases and it goes to 3D, 4D, okay, or 4F, what happens here? The screening of the S subshell is more. So electrons present in the S subshell, okay, they don't want to move out because they are having the maximum of the effective nuclear charge, okay, and yes, the pull of the nuclear charge is more, rather than we are going to the P, D and F. And as the result, what happens here? They try to hold the electrons within it, okay, and yes, they show a resistance of giving the electrons present in the S subshell, okay, and that is known as what? Inert pair effect, which we are going to see in this question of BCl3 and TlCl3, the showing of the higher stability of BCl3. Okay, so as you have now understood inert pair effect, okay, here this is being seen in case of this thallium trichloride. Okay, so in BCl3 we are seeing that yes, this D and F, okay, orbitals are missing, okay, and as the result, screening effect we are saying that it's not so efficient over here, because here this is small and d and f orbitals are missing. So here what happened, it can lose these 3 electrons, okay, which is in 2s2 and p1, and thereby having the oxidation state of plus 3, okay. And yes, here we are seeing it is having plus 3, but when we talk about what, thallium trichloride, its atomic number is 81, okay. Here we are seeing that yes, d and f orbitals are coming, isn't it, when we do the configuration. And yes, if d and f orbitals are coming, what happens here, we are seeing that yes, increase in the atomic number, okay, or increase in the size of this elements, okay, in the group from top to bottom. What happens, it is not neutralized due to the poor screening of the electrons present in the d and f orbitals. And as the result, what happens, we see in this that yes, in last it goes to 6p1, isn't it? So here it can lose this electron, but yes, here with the electrons which are present in the previous shell is present in the S subshell, and as the result this can give this 1 electron, okay, and thereby it can have plus 1 oxidation state. Thereby we can say that yes, if the compound is TlCl, okay, then yes, it is stable. But when we talk about TlCl3, here what happens, this poor screening of the electrons present in the d and f electrons, what happens, due to this, the effective nuclear charge for the electrons present in the S subshell, it increases, and thereby it does not want to give those electrons, it is holding that electron, okay, and yes, and as the result it makes it what, unstable in nature. So due to the inert pair effect which is acting in TlCl3, okay, is making it unstable rather than BCl3, where we are not seeing the electrons present in the D and F shells, and as the result here oxidation state quite easily we can see that yes, it has the +3 oxidation state and it is stable in nature, because all the 3 electrons which is present in the S and P can be given, but here due to poor screening of this D and F electrons, here what happens, inert pair effect acts, and as the result this TlCl3 is not stable. When we compare with TlCl3 and TlCl, okay, this is stable, because here which is present in the P, okay, subshell can be given, thereby giving it an oxidation state of +1. But yes, if it is TlCl3, okay, the electrons present in the S subshell can't be given easily out. Why? Because here there is inert pair effect acting over here. Now let us come to the second question, okay. It is what? Why does boron trifluoride behave as a Lewis acid? Okay. Now boron trifluoride, what is the formula? It is BF3. Okay. Now what is Lewis acid? Lewis acids are those which can accept the electron. Why? Because they have deficiency of electrons. So when we talk about boron trifluoride, boron, it has the valence electron of 3, isn't it? So if it has 3, and here naturally this fluorine has got 1, okay, and they just make bond with each other, but what happens? Still, is its octet complete? Nahi hai na beta. Here you can see only 1, 2, 3, 4, 5, 6. For being octet to be complete, it should have 8 electrons. So here there is deficiency of electrons. It needs 1 pair of electron more to be stable, or for its octet to be complete. So this molecule of BF3 is acting as what? A Lewis acid. So now coming to the third question, okay, consider the compounds BCl3 and CCl4, boron trichloride and carbon tetrachloride. How will they behave with water? Suppose a question comes in this manner. So how will you solve the question? Okay, you have to see that yes, how the compounds are. Here we are seeing, what we are seeing, that yes, if we see this structure of BCl3, okay, in this we are seeing that this is a electron deficient compound. Why? Because only 6 electrons are present in its outermost shell. Its octet is not complete. Okay, yes, and when we add water to it, what happens? Water, we are saying that yes, it has got lone pair of electrons, isn't it? So naturally it will try to take the lone pair electrons, okay, thereby it will be trying to become stable, more stable, forming what? Boric acid. And plus, here chlorine is also there, 3, so it will be forming HCl. Just balance it beta, okay. And naturally here we are seeing that yes, this BCl3 do reacts with water to form boric acid, as it is a electron deficient compound, okay, becoming thereby more stable in nature, forming boric acid. But when we talk about carbon tetrachloride, okay, here what do we see? That yes, here the octet is complete. It is an electron precise compound. So it will not try to react with water to form any other compound. Here hydrolysis of water with this carbon tetrachloride is not possible. So here what happens, how they behave? BCl3, yes, they do react with water to form boric acid, as it is an electron deficient compound BCl3. But as CCl4 is an electron precise compound, okay, it will not show reaction with water. So coming to the next question, beta, suggest a reason why the BF bond, boron and fluorine bond lengths in BF3 is 130 picometer and BF4 minus is 143 picometer. Okay, why there is a difference in the bond lengths of BF3 and BF4 minus. Okay, so when we are talking about BF3, okay, in BF3 we are seeing what? As sp2 hybridization. Okay, here we are seeing in this boron is having a Mt2p orbital. Okay, so let us again make the structure of BF3 if we are seeing, okay, BF3 if you see, okay, here it is having a Mt2p orbital. Okay, so what happens over here? These here also we see that electrons are present in what? The p orbital only in case of water, this fluorine. Okay, here what happens actually? In this boron, okay, they are forming sp2 hybridized hybridization. Okay, so this boron, okay, it forms the bond with this fluorine. Okay, but what happens here? In fluorine, there is cluster of electrons, okay, in this p orbital, okay, and as a result there is repulsion among the electrons, and this repulsion among the electrons leads to what? The back bonding, p pi back bonding. How? Here this fluorine, because here the electrons are more, repulsive forces are more, it tries to what? Donate the electron or transfer the electron to this boron. Okay, thereby what happens? Making it a double bond, p pi bonding. Okay, and this back bonding leads to this double bond, thereby what happens? Its bond length is 130 picometer. But when we are saying about BF4 4 minus. Okay, here which hybridization is formed? sp3. All the bonds are single bonds. Okay, and we all know that yes, if single bond is present, it has got more bond length rather than a double bond. So here, as all the bonds are single having sp3 hybridization, naturally this BF4 minus have a longer bond length than BF3, which has got, due to back bonding, what? Double bond, making it what? Only 130 picometer, which is less than BF4 minus, which is 143 picometer.